Hello and good afternoon, friends. Welcome to the CEC-UGC live lecture. Dear friends, as you know that from time to time we try to bring for you different subjects, and under these subjects we try to cater to your needs while discussing various topics. So dear friends, I would like to tell you all that today we are going to discuss on intermediate code generation, and not only in this lecture, we would be conducting more lectures on intermediate code generation, and I hope that these lectures would be beneficial for you. So dear friends, taking the lecture forward, I would like to tell you all that on this very topic, that is intermediate code generation. Today we have again with us in our studios Mr. Sarfaraz Masood. Mr. Masood is assistant professor in Department of Computer Engineering, Jamia Millia University. So first of all, I would like to welcome Mr. Sarfaraz Masood from Jamia Millia Islamia. So taking advantages from his experiences, let's try to understand about intermediate code generations. Over to you, sir.
Thank you once again, Skitika. In today's lecture, we'll continue our discussion on compiler design, phases of compiler design. Until now, we've talked about the analysis part of the compiler, and actually we are continuing on that aspect only. We have talked about lexical analysis, syntax analysis, and we were actually going on with semantic analysis. So in this very topic, we will be continuing further in semantic analysis, and I'll explain that why this topic, or why this separate phase. Actually, if we remember, we had that diagram of phases of compiler design, and we said after semantic analysis we saw that there was a separate phase known as the intermediate code generation phase. But in this lecture we'll try to clear out that doubt, that this is actually continuing with that same topic of semantic analysis. So in this lecture we'll try and understand more about intermediate code generation, what is this phase actually talking about, and how does it fit in to this compiler design phases component process. Okay, so in today's lecture, we'll try and understand understand more about intermediate representations. What are the various types of intermediate representations and how actually they are implemented, most of them. We'll talk about types of IR. We'll also talk about, I was just talking about, we'll also talk about IR implementations. We'll also try and understand about how IR is generated for assignment and declarative statements. We'll try and cover up these many topics in today's lecture. I definitely deeply acknowledge the various sources from which the examples and images were used for the purpose of the lecture, and I've been saying again and again that I've been following the Ulman Saidi compiler book for these lecture series. Okay, so we have seen this quite a few times, and every time we see this slide, we find some sort of a change that happens as compared to what we have initially talked about. The phases of the compiler, those 6 phases of the compiler. So that diagram is slightly changing again and again. We initially talked about the fact that lexical analyzer and syntax analyzer are working in tandem. It gives a token, it requests another token, so it's a parallel process that's happening, actually, pseudo parallel. The syntax analyzer will generate a parse tree. Now we have also talked about the fact that this parse tree will not be generated on its own. This parse tree will be generated with the help of the semantic analyzer, which is actually often embedded within the syntax analyzer. So this is very one important point that we all must understand. Otherwise we may find that semantic analysis phase may look like to be absent from this diagram. So because of that semantic analysis phase, we are getting this parse tree. So then we can see a very common situation that IR generator is kept as a phase separately. So this may look like a phase separately, but actually it is technically a part of semantic analysis only, because I initially said when I was talking about semantic analysis that whenever we try and say that we are converting one form to another, meaning or semantics is something that has to be associated with it. So IR generation is actually conversion of one form to another, so it cannot be done without the semantics or without understanding the semantics of it. So definitely semantic analysis is happening here also. So IR generator, we expect this IR generator to take in the parse tree or some sort of an abstract representation, and that is to be converted to an intermediate code. Once this code is converted, we've got two options. Either this is directly fed to the code generator, or we have an optional phase called the code optimizer. Definitely, if we get some time, we'll try and understand this code optimizer phase as well in the upcoming lectures. So in today's lecture, we'll try and introduce, or we'll try and start understanding this topic, that how this parse tree that we got from the semantic analyzer is getting converted into an intermediate code. So what are the different types of code and how is it getting converted to it? So these are the all aspects that we will be actually talking about. So architecture of the compiler was actually divided into two major sections, the front end and the back end. We have talked about it. lexical analysis phase, syntax analysis phase, and semantic analysis phase. And here we can see in addition that the semantic analysis phase is actually being talked about as a sub part of the the intermediate code generation phase is actually being talked about as a sub part of the semantic analysis phase. So we are still actually, this is what I'm talking about, we are still actually going on with the semantic analysis phase. This is not over, this will be over once this intermediate code has been generated. So one form converted to another, semantics part is then over. Then it will be handed over to the backend. The backend may consist of two phases, or it may consist of only one single phase, the intermediate code optimization phase, or it will definitely have a target code generation phase. So this phase is an optional one. It may be there, it may not be there, depends upon the priority that we want in our compiler. The front end of the compiler is independent of the underlying architecture. All these phases, they don't have anything to do with the underlying architecture. We talked about this. Hence, it can be reused for building up compilers for other architectures, whereas the backend depends upon the architecture of the machine. So we have actually, by dividing our entire task into these two major parts, we can actually see a large chunk of our compiler is now independent. In fact, the intermediate code generation part is also now independent of the underlying architecture. We do not need to bother about what's there at the machine level, or what kind of a code do we actually need to generate. We just simply need to generate till this. So all these 4-5 components of our compiler, the initial components, will all be independent of the underlying architecture. They're hardly bothered about what's there. So their design, their concept will not change if a new language, if let's say a new architecture comes up and we have to port our language to that very architecture also. So for designing a compiler for that new architecture, it's not a big of a hurdle. We just need to we just need to carry on with these 4-5 phases of our initial compiler design process, and then we just need to talk about distinctly about this target code generation phase, because this target code is actually the one that is dependent upon the underlying architecture. So the backend depends upon the architecture of the machine, not the other phases. So we have actually done what? We have divided into, this becomes a kind of a modular approach, that we have this module, we take this module as it is, and then we just try to alter the other module that is dependent. So independent modules and dependent modules, now we have divided our process into. So architectural options, as I was just saying, we may have simply lexical analysis, syntax analysis, and syntax analysis, by that I mean it's also having semantic analysis in it, and definitely by that we simply need to have one more phase that's called the object code generation or target code generation block. So only 3 blocks are good enough for us. Other option can be, we have lexical analysis phase, we have got syntax and semantic analysis phase, and we also do have something called the intermediate code generation phase, and we can see this optimization block is absent. So that is another part. As I was saying, that optimization, intermediate code optimization phase is an optional phase. You may have it, you may not have it, depends upon what priority do you expect from your compiler. You want an optimal code to be generated by the compiler, you need that phase. The other part can be something like this: the lexical analysis phase, the syntax analysis phase, intermediate code generation, and code optimization, and the final target code generation. So these are the various ways in which we can think about our architecture to be. Okay, so we've talked about this term quite a lot. Let's just learn more about it. Intermediate representation, as the name specifies, this is an abstract representation of the source code, such that it neither looks like the source nor like the target anymore. Now, it's a very simple way to understand. That's what it is saying, intermediate. Intermediate between the compiler had the aim with source at the beginning and target code at the end. So this is supposed to be a code that is neither like similar to source and not even absolutely like the target. So it's somewhere in the middle of that. It clearly expresses, it should actually clearly express all the information of the source, and conversion from here to the target should be a simple process. It should not be the case that we have landed up into a kind of a form that is now even more difficult to convert to target code. So that is something that we need to avoid. It can also express the target machine operations without indulging in too many machine details. As we were saying in the first line, that this is somewhere between the target and the source. So it should be having the properties of the source as well as the target, and should not have that many jargons as far as the conversion process is concerned. So it should be relatively simple. So if we think about a scenario where no intermediate representations are needed, in that case, let's say we have languages like C, C++, and Java, Pascal, and these are the following architectures. Let's say we talk about Spark, HPPA, x86, IBM PC. So if we would have been designing a compiler for Pascal or for the architecture Spark, we would have to go for a complete design. I mean, the initial part would have been same, the first 2-3 phases may be same, but rest of the part has to be completely specific to it. Similarly, Pascal for this very architecture, again we have to have a separate situation. Again we have to have a separate situation. Same goes for C, same goes for C++ or Java. I mean, one language, one architecture, we go for one kind of a compiler. One language, another architecture, for the same language we need to redesign the compiler to a certain extent. Then same for x86, then same for IBM PC. I mean, for all these different scenarios, I mean, if we tomorrow we have some different XYZ architectures, even in that case we have to add more. We have to have more changes in our compiler. So a number of changes. We can see a mesh being created over here. For each type, for each architecture, we have a separate kind of a larger section of compiler to be redesigned again and again. However, if we have an IR situation, then scenario will get quite a lot simplified. For Pascal, let's say we convert it to an IR, and from that IR we just need to convert to either of these forms. So this portion of the compiler is now independent. The only dependent part is this. So we need not redesign this many part. So this becomes actually quite a larger part. And in fact, IR is, I mean, the need for an IR is not just that the design gets simplified. We also know that because this process of conversion is an automated process, it's an algorithm based process. The chance of getting the most optimum output code or the most optimum result or the most optimum target code for a very optimized source code may not be that very high. So there are chances that the code that you have generated by conversion, by algorithmic conversion, that may have a lot of chance of improvement as far as the time and space complexity is concerned. Although we may boast about the fact that yes, we have designed the best of the possible code, we have designed the best of the possible, we have given the best of the possible logic to our code, it's using the minimum number of variables. But even then, because this conversion is not guided by, I mean, this may be guided by us, but this is not actually done by us. It's actually done by the help of some algorithm within the compiler itself. So there's no guiding criteria over there that we can at that very time we can interfere and we can say, no, why are you using this variable extra, why are you performing this operation again and again. So there are many chances, we will see later on in the upcoming lectures, that there are cases when for a very optimal code we may land up in 2 different or 3 different cases of target code possibilities. So that is, it means that there is a large possibility of optimization. So IR not just gives us the advantage of modularity, but also helps us in if we provide that IR optimization phase, then it also gives us a very large possibility of optimizing our target code. So it optimizes the intermediate code, the optimization phase, and that too, I mean, because we have an optimized intermediate phase result, so that will also help us in achieving an optimized target code result. So these are the 2 major advantages we have, modularity and the optimization. So as I was talking about, intermediate code eradicates the necessity of writing a completely new compiler for each unique machine architecture, as the analysis part of the compiler remains unaffected, and even in analysis part we now see that we also have one extra phase, that is the intermediate code generation phase. So that is also not supposed to be rewritten. Only the second part, that is the synthesis part of the compiler, needs to be changed as per the target machine. The task of applying optimizations on this code now becomes pretty much easy. These optimizations improve the code performance in terms of execution, time, space occupied. So one thing I wanted to make clear over here, that these optimizations which are actually making your code perform better are not because of the fact that we made our code poorly. I just gave an example that we may have made the best of the possible code with the best of the possible algorithm, but because this conversion thing is happening by the system, so there is a large possibility now open where the system where this output can be optimized. So here we get this option, and the optimization task actually is relatively very simple or easily possible when it is applied on IR. If we have an IR, its optimization is relatively simple as compared to the fact that if we think about optimizing the target, or if we think about optimizing at any other different levels. So what are the major considerations when that we should actually talk about while designing in an IR? The major consideration while selecting an IR for the compiler can be when to use an existing IR. There's an already available IR. Should we go for that? Should we design our own IR for this very language? It depends if the target machine architecture is pretty much similar. Also, if the new language is also similar. The question being put up in this point is that we are talking about a new language, and then the question is we have to go for an IR. Now, should we go for the well-known standard IRs that are already available, or should we design our own IR? So, these are the two questions to be answered. If the after architecture is similar, we may go for the existing IR, or if the new language that we're talking about is also similar to the existing language, then also we can go for the same IR that has been implemented till now in other setups. Whether the IR is suitable for the optimization that are intended to be performed, as some optimization may take much more time than they would on a different IR. So that is also one very important aspect. We should have a very clear-cut situation that, okay, if we talk about this IR, then this IR may not be allowing us freely to apply these optimizations. And if these optimizations are something that will be very often required in my code, then we need to think about it. So there are certain optimizations that can be performed only on certain IRs and not others. So we have to be pretty clear about it. While designing a new IR, we need to take into consideration the following points. If we are not using the well-known IRs, the well-known intermediate representation, and we are designing something new, then we should actually be thinking about these very points also. The level of machine dependence, how much dependent on machine it will be, its structure, its expressiveness in terms of it expressing the source priorities, and it expressing the machine dependencies also. Appropriateness for general and special optimization, appropriateness for code generation. There should also be a question that is this the only IR that will be used, or there will be multiple IR? There are cases in compiler design where not just one but multiple IRs are used for the purpose of target code generation. So different forms are actually considered. That's what the point is saying. Okay, some examples of IR. Some of the well-known intermediate representations are actually can be talked about in these following categories. They can be graphical representations, for example, syntax trees, parse trees, directed acyclic graph. These are also intermediate representations. These are actually the forms in which our source code is represented intermediately, and these forms are actually the graphical forms. These are not the non-graphical forms. You will find some, that's why we can see these word tree and graph. So these are the graphical forms in which we can have our intermediate code. Then we have another representation, that's the non-graphical representation category. We have the postfix notation. It's a very well-known notation in which we can also represent our intermediate code. It's a very strong notation actually. It's a very important notation that is also utilized quite a number of times. Then we have another category called another name called the SSA form, the static single assignment form. Another important form, another important well-known IR. And the IR that we are going to talk about in details in these lectures and the upcoming lectures, that is a 3-address code. So it's a special type of intermediate representation that is carrying, again, as per the definition, all the details of the machine level and as well as the details of the source level. So IR should have individual components that describe simple things. So these should be simple in nature. Okay, some examples of the IRs in the modern day compilers. GCC is a very widely used compilers. That's found in the Linux and the Unix architecture. It uses two IRs actually, the parse tree and the register transfer language RTL. And also in some cases we can find the tree and the static single assignment combination also being used. Then we all know that Java is a very famous example whenever we talk about intermediate representations. We may not have known much about GCC and Turbo C, but we definitely all know that Java explicitly gives us the output in terms of the byte code that the rot class file that actually we get, and that is to be then given to the interpreter, which then gives us the execution part of it. So the byte code is actually the intermediate form. This is the one that actually makes it independent. We always associate this word of machine independence with Java. This is the very reason, because they have said, they have given us this byte code, and now this byte code is actually not dependent upon any of the underlying architecture. The byte code that we have achieved on one architecture can be simply taken on to the other architecture and then executed from there itself. But the trick is that on the different architecture, we'll have a different virtual machine, the component that will actually run this bytecode. So for different machine, they've given different components, different virtual machines, the same bytecode taken up from, let's say, a Windows machine and taken onto a Linux architecture, let's say, and then it's being executed there also. Some programming languages have well-defined intermediate languages and also some separate components to process them further. As we were talking about Java, the bytecode actually it requires a Java virtual machine. For Prolog, we have something called the Warren abstract machine. In fact, there are bytecode emulators to execute instructions in these intermediate languages. So definitely we need a component if we have an intermediate code. Then we need a component that will understand this intermediate code and then help us in achieving the object and the target code. So we were getting the IR in terms of, let's say, a parse tree or an abstract syntax tree, and the intermediate code generator is actually giving us the IR, let's say some 3 address code instruction. So it can be a direct translation using the syntax related translation schemes, parse tree to 3 address instruction, that can also be a case. As far as conversion is concerned, it can be done while parsing in a single pass. That can also be possible. While we are parsing, we know this is the time to shift and to reduce, and we have done, if you remember, the evaluation of the attributes is done while the reduce operation is being performed during parsing. So at that very time, we can also perform these translations. Needs to be able to deal with syntactic errors and recovery. Those are the components that we have. Those are the elements actually that we also need to be sensitive towards. We can have an indirect translation also. This conversion can be an indirect one. First, validate the parsing by constructing an abstract syntax tree. First, you would perform that thing. It uses SDT scheme to build an abstract syntax tree. Then traverse the abstract syntax tree and generate the 3 address instruction. That can also be another way of doing it. So this slide is actually talking about the abstract syntax tree, how it is being generated. So this is just a recap of what we have done in the earlier lecture. We talked about this part, that how the syntax tree will be generated, or an abstract syntax tree will be generated. The abstract syntax tree, we said that these are the semantic rules that need to be executed so that we actually start getting an abstract syntax tree for a certain code. So this is the grammar, and these are the semantic rules. We've done this. It's a make node function. It was present in 2 forms: make node for an interior node and make node for kind of a leaf node. So that there we said we have the name like make leaf. So these are the actual semantic rules which will be executed when the corresponding production is actually being reduced. So when we reduce this, I'm talking about one of the options. The other way, we have a complete parts. We generate this abstract syntax tree, and then after a generation of this abstract syntax tree, we traverse this syntax tree, and then at each node we apply the corresponding production. We apply the corresponding semantic rules that are mentioned, and the 3 address code or whatever intermediate representation we are actually trying to achieve will be generated. If you only talk about the syntax tree as an example, syntax tree for, let's say, the case x is equal to minus b plus y star z plus y star z would be something like this: x is equal to y unary minus plus y star z and y star z. And the other intermediate, this is one of the intermediate form. One intermediate form will be achieved by abstract syntax tree. Another intermediate form is actually the syntax tree, which will look something like this. And the other intermediate form, the graphical form, will be directed acyclic graph of the same example that we have talked in the last slide. It will be something like this. So unary minus y star z, y star z, and as we can see over here, this y star z, instead of being talked about again, is being simply referred, and for this very node we are having more than one parent. One parent is this and one parent is this. That is why this tree is now no more a tree. This is now a directed acyclic graph. This is more like a graph, because in tree we have a simple rule that one node will have one parent. It may have multiple children, but it will have only one parent. So this rule was violated. So now it's no more a tree. It's better to be called a directed acyclic graph. So this is another way we can represent our represent our source code. For this, we need to actually change our make node function of the semantic rules that we were talking about. So while constructing a syntax tree, if we slightly modify our make node function, then we can achieve the directed acyclic graph pretty simply. And how it can be done, before making a new node, just try and see that whatever whatever value, whatever components you are fetching into this make node function, have they already been, the node that you're trying to design or make, has it already been constructed or not? If it has been constructed already, no need to create it, simply refer it. And within an expression, there is very less possibility that the value of a variable will change. If you think about a code, the value of, let's say, variable y may change at multiple locations. But within an expression, the variable's value change, it's very rare, except for certain cases. So y star z within an expression ideally should yield the same result. So y calculated 2 times, simply refer it. So that is an advantage we get with directed acyclic graph. Definitely, a code generated by this will be slightly more in terms of time and space, will slightly be more complex in terms of time and space, because this operation will require time, this operation will require time, both of them will require space. However, in this case, only one space is required, only once it will be executed, the other time it will only be referred. So a code generated by the help of a DAG will be much better as compared to a code generated with the help of a syntax tree. So if we are using a combined structure, that we have a combination of tree and SSA or tree or tag, something like that. So in that case, a DAG will be definitely a better option. But the cost of constructing a DAG is definitely quite high. It's easier said than done. We're simply saying that whenever you're trying to make a new node, please see, has this node already been created or not. Now, just by saying this one simple line in English, it's pretty simple to say. But when we go at the algorithm level, that check whether this node has already been created or not, you will have to compare with all the n-1, all the n nodes that you have constructed till now. So at every new iteration, a new node will be added to the tree. And if at that very time you have to ask this question, then this question will be asked now n number of times. So at each iteration, this n is increasing. So it's a very large complexity that we will get for each question that we ask from the system, whether this node has been created or not earlier. So at times it's kind of a confusion whether to go for DAG or not, because we've got some other techniques by which we can later on try and eliminate. So this is not the only time when you can eliminate this reoccurrence of expression, sub-expression. We have optimization like sub-expression elimination, common sub-expression elimination that can be applied if we have a target, if we have an intermediate code in form of 3 address code, we can apply that. So it depends upon the cost that is being that is coming for that operation. So going on the series, another intermediate representation is the postfix notation. That is another very well known common notation in which we can represent our source code. Mathematical notation wherein every operator follows all of its operands. So it's a very simple case. Postfix, the operator will follow the operands. So if we just try and understand by the help of example, it was, let's say, 19 divided by 25 plus 32. So 25 plus 32 was to be done first, and then divided by, should be the new denominator for 19. So this can be something like this: 25, 32 plus, this operation goes first, and then whatever result comes, that will be the other operand for divide. So 19, this operand divide. So this is the corresponding postfix notation for this mathematical expression. Another example that we can take is x plus y into a minus b, and think about it. What can it be? It will be simply xy plus ab minus, and that it will be star. Xy plus, because this operation to be done, then ab minus, then this operation to be done. This will be followed by a multiplication of this entire component. So it will be xy plus ab minus star. So if you simply try to formulate the rule, it will be, if e is a variable or a constant, then the postfix notation of e is e itself. That will be itself again, if it's a constant or a variable. If e is an expression of the form e1 op e2, then the postfix notation of e will be e1 e2 op, as I was saying, that the operator will follow the operands. E1 and E2 are postfix notation of E1 and E2 respectively. So if E is the parenthesized expression of the form E1, then the postfix notation of E is the same as the postfix notation of E1. So this was just a kind of a relation situation of E and E1 in this case scenario. So the major point to remember is actually this, that E1 op E2, so it will be E1 E2 op, where E and E1 are the intermediate representations of them itself. So here we get the answer, x plus y, xy plus, a minus b, ab minus, and then star. So we have the answer over here. Okay, so going in the line, we have the next form, that is the static single assignment form. The static single assignment form is an intermediate representation that facilitates certain code optimization. The main point actually of difference is this line. All assignments in SSA are to variables with distinct names. Hence the name static single assignment. You can see the case over here. P1 is equal to A plus B. Q1 is equal to P1 minus C. All the names are unique. I mean, they have to be unique in this case. Q1 is equal to P minus C. P2 is equal to Q1 star D. And P3 is equal to E minus P2. Q2 is equal to P3 plus Q1. However, in this case, I mean, if we try and compare it to three address code, three address code, we can have the same name coming up again and again. The P being done over here, P is equal to A plus B. The P coming again over here, P is equal to Q star D. The P coming in again over here, P is equal to E minus P. So this is a certain form that is allowed in three address code. However, if you try and contrast it to static single assignment, it will be one single time. Only once you can do this assignment, not the other time. It's good for certain type of optimizations. Certain optimizations are there for for which SSA is pretty much suitable. So these are the aspects in which it is different. Finally, we talk about three address code intermediate representation. The three address code intermediate representation is actually the one that we'll be talking in details in these lectures. As the name suggests, three address code. It's a code in which each statement will be talking about at most three addresses. Something of the type x is equal to y of z. So z, y are operands, x another operand, so three operands at max. The minimum operation that we can have is x equal to y, the copy operation. So construct map to three address instruction register based IR for expression evaluation. Infinite number of virtual register we can have, still independent of the target architecture. That's the best part about it. The most generic statement format will be label. We can also have a label for each statement, x is equal to y of z, where this operation is the operation that we have specified in the expression, and this is the assignment operation that will be there by default. So x is equal to y of z, three expression we're talking about. Or we can also have a different form of it if expression go to L. That's another way in which we can find these three address code statements. Statements can have symbolic labels. Compiler inserts temporary variables. We can have temporary variables. Type and conversions dealt in other phases of the code generation. So let's just quickly go through the different types of three address code statements. We can have assignment statements which can be of the binary form, x is equal to y of z, which can be of unary form, x is equal to op y. For example, we have unary minus. The op can be any reasonable arithmetic or logical operator. We can have something called the copy statements, something like x is equal to y. We can have a copy statement of the type index x is equal to yi, where actually we are talking about the index scenario that pick up the element, put y locations away from the base address, I locations away from the base address y, something like that. We can also have the index scenario something like xi equal to y. The address and pointer manipulations are also allowed. These are the valid three address code statement, x is equal to ampersand y, talking about the address of y, x is equal to star y, that is the pointer situation, and we can have it in this form also, star y equal to pointer x is equal to y. So these are the valid three address code. These are various types of three address code statements we have: assignment, binary, unary, copy, simplex, indexed, address and pointer manipulation based. We can also have some jumps. Definitely it won't be complete without jumps. We do have a lot of jumps in our source code. So to have a counterpart of those in our three address code statements, we have jump of the type unconditional jump, that is simply by writing go to L, where L is a label that we have specified within our code. So whatever the label will be, it will simply jump to that very location. Then we have something called the conditional jump. You do jump, but on a condition. It's specified in the general format of the type if x relop y go to L1. So this is an expression, the conditional expression that we were talking about earlier. If X relop is a relational operator, Y go to L, which is again a label, and then this part is optional to be written in the next line, else go to L2. If we do have a situation that we can only have an if in our source code, we do not have an else. That's not necessary to have an else. So this is what is being specified over here. We may have an else, we may not have an else. The next line to be followed will have it or not. So where relop is any relation operator less than, equal to, greater than, or something like that, anything like this. And then we can also have statements of the type the procedure calls, because in our source programs we also have procedure calls, something like this: p is equal to x1 x2 up till xn. So this may be represented as something like this: param x1 param x2 up till param xn. Here we are specifying the parameters, and then we simply say a statement call p comma n, where n is the number of parameters that we have specified in the up lines. So the above n lines are actually talking about the parameters, and this is the function in which we have to call. So this was the one line statement that we do in our source program. This is the corresponding situation that we need to have in our intermediate representation. So param x1, all these are the parameters, the n parameters, and this is the function that we need to call. Again, you can see the basic law is not being violated in any of these cases. 3 address code, maximum 3 addresses, 1 2 3 1 2 1 2 1 2 3, that's it. Again, and over here 1 2, maximum third. If you go to minimum, that is only 1. Even over here, in this case there were multiple in the same line, but we have simplified this in the intermediate level. Only one address, another, and over here maximum 2 names are coming up. So the basic law or the basic rule that was specified in the name of this form, the 3 address code, is not being violated anywhere. Just to have a quick example. For example, we have a code snippet for I equal to 0, I less than 5, I plus or plus I, whatever we need to specify, followed by this one statement bi is equal to I star I. So very simple or a naive 3 address code can be. First of all, ask yourself, the first of the thing to be done in a for loop is initialization. So that line will be there. So I equal to 0. So let's say we have a temporary variable ti corresponding to this I, and we are saying t1 equal to 0. The next line to be executed in a for loop is the condition. So now comes the condition. So if t1 is actually referring to I, then we will have to have this line: if t1 is greater than equal to 5, then go to L2. Let's say we have this corresponding situation. So this is greater than equal to 5, then go to L2, where actually L2 is a label. So if this part is true, I is this is less than 5, I guess this is some sort of a doubt in this condition. So this actually has to be same, nothing else. If this is less than 5, then go to the label. So if this condition is true, we have to jump somewhere. So this is what it is saying, that if t1 is whatever this condition was, 5, then go to this place L2. Otherwise we have to be here. So one way is actually, if it is less than 5, then we have to go to this part. If it is not less than 5, then we have to go here, outside the for. So actually this part is being written the other way around, more typically, that if it is against this line, if I is less than 5, however it's saying if t1 is greater than or equal to 5, that means violating this rule, then you have to go to L2, simply jump out. Otherwise, if it's wrong, then you have to jump in. So it's actually talking about the same condition, but in the other way around. So if I is less than 5, this condition will be false. If it will be false, you will land up over here. The next line, t2 equal to t1 star t1, because we have to evaluate this I star I. This cannot, over here, if you look at this line, 1 2 3 4 addresses are being referred. We cannot refer them in one single line. So we're simply utilizing a kind of an indirection. T2 is equal to t1 star t1, and then we are simply saying b t1 is equal to t2. So these two lines actually they come together and they form this very one single line, followed by t1 is equal to t1 plus 1. Why? Because once the body is over, the next line to be executed is increment decrement. So initialization, condition, if true, body, if false, outside body, and then once the body is executed, we come back to the initialization to the increment decrement part. So we increment this thing as per specified over here, and then once it has been incremented, we do not jump out of the loop. This is no point to jump out of the loop. We come back to condition. So now it's saying go to L1, go back to the condition. and do it again. So this is kind of a intermediate form of a small single for loop that we have specified over here. However, actually we're just trying to, I mean, this could have been done simply by saying T1 is less than 5, then go to this position, else we would have utilized an else actually. So I mean, we have, this is a code that is actually not specifying an else, it's actually doing the same task without using an else. So quickly we talk about the various implementations of three-address code statement, how actually we implement them, how they're actually seen. There are three common implementation of three-address code. One of them is the quadruple, another one is the triple, and the final one is the indirect triple. Let's just consider a simple case, a single common case, and we'll try and see for each of them that how they're different. So quadruple is actually a record structure with 4 fields. In quadruple, that's why the name is saying quad. Quad means 4. One of the field is op, another field is argument 1, next field is argument 2, and the final field is result. So op, argument 1, argument 2, and result. The op field contains the operator, the statements having unary operator do not have argument 2, obviously, because for any statement, if you have got a unary operation, then unary operation do not have 2 operands, they have single operand. So for single operand, they will not have the operand 2. So argument 2 field will be empty in terms of unary operators. Operators like param use neither argument 2 nor result. The target label for conditional and unconditional jumps are in result. It's a very important point. Whenever we have jumps, so jumps have labels. So the labels for unconditional and unconditional jumps are actually in the result part. The contents of the field argument 1 and argument 2 are result are typically pointers to the symbol table entries. If so, temporaries must be entered into the symbol table as they have created. Constant actually have to be handled differently. Let's just understand this example, and it will be pretty clear to us. So we had this expression x is equal to b star minus c plus b star minus c. So if we look at this one single source code line cannot be possibly one single three-address code line, because there are multiple addresses being talked about, 1, 2, 3, 4, 5. So I mean 5 different addresses are being talked about. We cannot get them together in one single line, we'll have to break it up. So we'll try and see which is the minimum operation that should be done first. So we can see over here, if you try and see the right hand side, minus c is the operation, or unary minus c is the operation that needs to be done first, followed by the next minus c, followed by b star minus c, followed by b star minus c, followed by the addition of these two. So correspondingly, we have found these 5, 6 lines of three-address code. So let's just get back to three-address code. We can see the first operation, statement number 0, is unary minus, argument is c, and the result is now being stored in T1. So a temporary we have specified, and this temporary is now actually holding the value of this unary minus c operation. And as we can see, argument 2 is empty. Next line, we have the solution for this. Now the solution, now we are trying to operate this part, b star minus c. So the next statement is operation is star b T1. This minus c is now no more minus c, this is now T1. So T1, and the result of this thing is now being stored in T2. Next, we're trying to solve this part, unary minus c, again star b T3, because earlier this was T2, now this is T3, a new temporary being assigned, and simply we have. So we have the result of this in T3, we have the result in this of T4. So the final statement is actually, the fourth statement is now actually talking about plus T2 and T4. This result, entire result is now residing in T2, this entire result is now residing in T4. So we simply say T2 plus T4, and the result is actually going to a new temporary called T5. So now we need to add just one more simple line, x is equal to T5, and by that doing so, the complete evaluation of this right hand side will be done, and the answer will be given to x. So these are the three address code statement that we will find, and in quadruple structure we will find them in this format. 4 fields, op, argument 1, argument 2, and result. However, this can be reduced. This table size can be reduced by having a different form, by having a different implementation called triple. In triple, as the name suggests, we've got only 3 fields, the op, the argument 1, and the argument 2. This helps us in avoiding the need of entering the temporary names into the symbol table. So let's come to the example and try and understand this. So we're simply saying again, minus c, good enough, no result. We're not storing the result at all. So where does the result go? Actually, now we're trying to refer it by the help of the statement or the pointer actually. The pointer to the symbol table for the entry defined in the program, the pointer to the triple structure which are for the temporaries used for the construction. So here we can see that we are having pointer to the triple entries. So this argument 2, in earlier case, the argument 2 was something T1, okay, this T1 was stored, T1 was referred, but here we are not storing this result anywhere. So now by saying 0, we are saying actually this is a pointer to the triple entry 0. So this is having the same effect as star B minus C. Next statement again minus C. Now this is being referred by 2. So star B2, that means a pointer to the triple entry true. Finally, we have this entry as over here we'll have the entry as 1, and this entry will have been as 2. This should have been simply as plus T2 and T3. Finally, the assignment operation comes, and this result of statement number 4 is being transferred to X. This statement should have been slightly different. There should not have been a case of T2 and 3. Okay, no issues. So we're just trying to eliminate the result part from here. There's no result part. We're just trying to refer these result by pointing to the triple entries simply by that. So this is good. I mean, we have reduced one column from it. Reduction of column means reduction of space, so triple seems to be better. Similarly, we can, if we try to talk about one special case, index assignment requires 2 triples A, I, B. So that is the ith element from the base address A that will have the value B. So we can say that it will have now actually 2 triples. One for this AI, that means ith element from A. This is the operation, and the next operation will be saving. I mean, this will be the reference to it. So this is equal to B. So this will actually become AI. This is actually nothing but AI equal to B. So we felt that this fact of triple is pretty good. I mean, we do not have to have those temporary names, and we can simply refer them by the pointers. But think about a case where after this implementation we have to do optimization. If this would have been quadruple, look at this, if this would have been quadruple, then in case of quadruple we are all talking about temporaries. If we remove this line, let's say we are removing these 2 lines, because these 2 lines are nothing but the same, these 2 lines. Let's say for example we are removing line number 2 and line number 3. This will not affect anyhow, only these references T3 and all those will be eliminated, but there will not be much of a confusion. However, if we remove an entry from here, all the references of 2 will have to be adjusted. So a massive amount of change will have to be done, a massive amount of reconstruction will have to be done in terms of this, because over here we are not talking about some temporaries T1, T2, T3. We are actually directly referring to some triple location. These are pointers to the triple entries. These are not temporary variables. So a slight change or a slight removal of this statement will have a very disastrous effect. We'll have to do all those changes correspondingly. For example, this statement has been removed. So statement number 3 has now become statement number 2. So everywhere where statement number 3 was being referred, now we have to write statement number 2. This has to be done in the entire code. So this becomes quite a cumbersome thing. So by removing one statement, we are not achieving much. We are actually landing into a different difficulty. So it's better to have something called an indirect triple. So indirect triple has something like this. Indirect triple adds a list of pointers to triples so that the triples can be shared and moved easily. That was a major problem in triples. So as we can see, x is equal to b star minus c plus b star minus c. We can see that this is the basic triple that we are having. To this we have just added one simple statement, list of pointers to the triples. By this the movement becomes actually slightly simple. But then by doing indirect triples, we are actually coming back to the same situation of quadruple. We are having in fact more number of columns. We can see 1, 2, 3, 4, and then we have the statement part also. So actually it has come back to something similar to quadruple. So it's not wrong by saying indirect triples are very much similar or like quadruples as far as their utility is concerned. These two implementation require about the same amount of space for a certain code. Also, they are equally efficient for the purpose of reordering of the code. However, the indirect triple can save some space. This is the major point actually. We can save some space as compared to the quadruples if the same temporary variable is actually used more than once. The reason is that 2 or more entries in the statement array, this statement array, 2 more entries in the statement array can point to the same line in the op argument 1 argument 2 structure. So this is where indirect triple actually does the trick. It by taking a similar or same amount of space as taken by quadruple, it slightly overtakes it by doing it better in this way. So we quickly talk about the first type of statement that you find in our, now we actually moving on to processing of declarative statements or processing of our source code. So the first of the statements that we normally find in our source programs are declarative statements. So what is to be done when you find some declarative statement? During the processing of declarative statements, the following important steps are taken. Entry to the symbol table is done actually. Allocation of space for the components in the program and recording them in the symbol table is done, and generation of appropriate code, intermediate code wherever required. So largely what we see is that then the first of the two operations are largely being performed whenever we find a declarative statement. Whenever we have a statement of the type int a comma b, then these two operations, entry of the things into the symbol table and allocation of their space, is largely done. We may have some statements where even assignment is also allowed, int a equal to 0. So int a may not require a 3 code IR implementation. However, a equal to 0 will require a 3 code implementation. So whatever appropriate code is to be generated, that has to be generated accordingly. So quickly taking an example, or actually this is the SDT, the syntax directed translation scheme for declaration statement. And just to give you a quick overview, in this entire setup we cannot find any 3 code being generated, because this is actually only talking about the declarative statements. So P derives D, D derives D, D derives ID and T, T derives integer, real. This is the same example that we have been talking about till now. So you can see over here, all it is doing, actually enter is the function that is doing an entry into the symbol table. So enter ID comma name. The moment it identifies the type of an identifier, the moment it gets a type of an identifier, it does an entry. So at this production, you have to do an entry into the symbol table, that id.name, t.type, whatever the type, and offset. Offset is actually a value that we are taking so as to decide the next starting location, the next address of this variable. So initially, when we are starting with declaration statement, we are saying offset is equal to 0. So the first variable at address 0, the next variable offset updated, the next variable offset updated. So offset is actually the value by which we are trying to guess the corresponding location that this variable will have. So all we are doing over here is this specifying the type, specifying the width, and specifying the other value that we are extracting. So largely declarative statements do not much add to the 3 address code. We do not find any corresponding 3 address code of declarative statement. But if declarative statements are actually coming up in the form of assignment statements also, then they will have their corresponding effects. Okay, so this is a slide where actually I would like to stop for this lecture. This is the slide from where we will move on in the next lecture. Here we'll start actually talking about, because we have done some discussion on declarative statements. The next statement that we actually encounter in our source program are the assignment statements, the more largely found statements. So how assignment statements are converted to corresponding 3 address code, what are the semantic rules that are applied or that are actually executed by which we get those 3 address code, will be actually done in the upcoming lectures. So in today's lecture, we did types of IR, 3 address code, types of 3 address code statements, implementation of 3 address code statements as far as quadruple, triple, and indirect triple is concerned, declarative statement, and definitely we have left ourselves with assignment statements. References and for further study, we can, as we have been saying again and again, compiler principle, techniques, and tools from Alfred Aho, Ullman, Sethi, and Monica Lam, and also another good book by Engineering a Compiler by K.D. Cooper and Linda Togson.
With this note, thank you, sir. Thank you so very much for giving a precious time as well as a precious input to this particular lecture. As Mr. Sarfaraz Masood himself said, we would be continuing further in our next lecture, and we would be discussing more on intermediate code generation. Till then, friends, if you have any queries or if you want to give your feedback regarding this particular lecture, then you can mail us at info.cec@nic.in. We would love to solve your queries next time when Mr. Masood visits our studio. Till then, take care. Thank you, sir. Thank you so very much.